Hi, Kareem Mazni here, and today I'm going to talk about the Scrypt algorithm. It's a password-based key derivation function that is used cryptographically to prevent passwords from being hacked by both brute force and rainbow table attacks. So, let's dive in.
Hi, thanks for joining. Today we're going to talk about the Scrypt password-based key derivation function. So oftentimes, when a user creates a password, it is run through a hashing function like SHA-1, SHA-256, MD5, or some other, and a password key is generated, which is stored in the database. So the word CS breakdown would be hashed into the following key. The benefit to this is that if the hacker who tries to break in is armed with the hash, they are unable to reverse engineer it to get back to the original plaintext, which is CS breakdown. And the plaintext is not stored on the database at all, so that gives that extra layer of protection from the plaintext ever getting compromised. Now, if you're logging into some super awesome website, it would create a database call based on your username to pull up the hashed password. Then your password would be fed through a hash function, and then it would check to see if the hashes match. Hashed passwords like this are still susceptible to brute force attacks, where an attacker will try password after password after password until they find one that works, or rainbow table attacks, where they reference a large table of pre-hashed passwords and try them against the database. So to make it more difficult for a brute force attack to happen, we'd add something called SALT, and that's a large sequence of additional characters which are combined to the password, and then this combination is fed through the hash algorithm to create the password key. However, this can still be susceptible to rainbow table attacks. Now this is how rainbow table attacks work. So when an attacker is trying to brute force attack, and they try password 1, for example, they'll feed it through the hash function and then try it directly with the database. If that doesn't work, they'll try a different password, password 2, feed it through the same hash function, and try again. They'll continue on until they find a password that works. Now, because it has to hash every single time, this is computationally expensive. However, it has low memory requirements. On the other hand, a rainbow table will make a table of the passwords that have already been tried as well as their hashed values. So when the attacker tries a new password using brute force, they'll store that password and hash in the table, so in the future, when they're trying to hack different passwords, they'll just quickly reference the already hashed password from the table into the database, which will save on the computational expense required to hash each and every password. This is computationally cheap. However, it has high memory requirements. But with the rate at which hard drive space quickly becomes cheaper, rainbow table attacks become really feasible for outdated systems of encryption. So now there's another type of encryption called password-based key derivative functions. And this takes the password just like the hash does. It also takes SALT, and a number of iterations value is specified. So these are fed into the algorithm, and the algorithm will generate a password key. Now the SALT is not combined to the password outside of the function. It's passed in untouched, and in the function it gets combined. And the function performs a pseudo-random function inside to the password data in a loop, and the number of iterations of that loop is specified by the user. Building a rainbow table that's large enough now takes too much time to be feasible, because this process is relatively slow. It's fast enough for a user to use legitimately, but when you try to use it at the large scale that hackers try to use it, then it becomes prohibitively slow for them to build a good rainbow table. However, these can still be attacked by large parallel operations. So a new way was needed to combat parallel attacks. And this is where the Scrypt password-based key derivation function comes in, also known as Scrypt PBKDF. It was created by Dr. Colin Percival, who studied mathematics at Simon Fraser University in British Columbia and got his doctorate at Oxford University. It was originally developed for his Tarsnap online backup company, which has Amazon as one of their largest clients. So the gist of it is that it's a memory-intensive algorithm that makes it costly to perform large-scale hardware attacks. It was published by the Internet Engineering Task Force in 2012, so now it's public and widely available to use, and as such, it's used by popular cryptocurrencies like Litecoin and Dogecoin. So let's break down the Scrypt PBKDF algorithm in more detail. So it too takes in the passphrase just like the other hashing and cryptography functions did. It takes a salt value, but it also takes a CPU cost parameter, a memory cost parameter, a parallelization parameter, and the output length is specified by the user as a variable called dk length. And out comes the password key. And this is what a hexadecimal valued password key would look like from the hash CS breakdown. So what makes Scrypt different from a regular PBKDF? Well, the parallelization factor helps you fine-tune the relative CPU cost. The output length allows the user to have the ability to define the output size, and NNR allows the user to set the CPU and memory cost. So what's left out of this is that specified number of iterations of that pseudo-random function inside. That is calculated by taking certain values from N, R, and so on. The inner workings have a lot of differences as well. So let's break this down and go through it step by step. So the first step is to create an HMAC, which stands for a hashed message authentication code. The next step is it performs a widely used password-based key derivation function called PBKDF2. Then, in a loop, it'll do a memory hard function called smix, and we'll go into detail on what that entails later. Lastly, it'll do the PBKDF2 function again, and then the algorithm is done. So let's get started to look at what HMAC does. So MAC stands for Message Authentication Code, and it's a type of digital signature. So let's quickly go over digital signatures. Say you have a document in the real world. Let's say it's a university degree. The signature on the paper is what gives it a lot of its validity. In the digital world, you might have a digital file that too could use a signature. To do this, a user would specify a private key, and then they would run a signature creation function using their private key on the data. Then a signature would be created. So, let's say Alice and Bob want to communicate a signed document. So Alice will send Bob her public key plus the data and the signature. Bob wants to verify that this document does indeed belong to Alice. So he'll run a verification function on Alice's public key using the data and the signature, and it'll return either true or false. True, meaning that it really was signed by Alice. False, meaning that it's not. So now let's take a look to see how a MAC works. So we have Alice and Bob. The first thing Alice does is she sends Bob her private key through a secure channel, which is protected from any hackers intercepting it. Now, let's say she has her data and a private key. She'll feed it through a MAC function using both her data and private key, and it'll output a value M. So now she sends Bob the data and M. For Bob to verify this, he creates M prime, which is using the MAC function, using her key and the data, and then he just simply checks to see if M is equal to M prime, true or false. Now let's take a look at a MAC from a hash function, also known as an HMAC. So she also sends the private key to Bob through the secure channel. And now she has her data and the private key. She'll feed it through the HMAC SHA-256 algorithm, which performs the following operation. So there's a hash function on the outside, and on the inside, it takes her private key, and she XORs it with the outer padding, and then concatenates the result of that with the hash of the private key XORed with the inner padding concatenated with the data. So H stands for the hash function, which in this case is the SHA-256 hashing algorithm. OPAD stands for outer padding, and IPAD stands for inner padding, and K is the private key. So now Alice will send Bob the data and this HMAC hashed value M. Bob will try to calculate M prime, which uses the exact same function, appending data and K. He'll also check to see if M is equal to M prime, and if it's true, then the message does belong to Alice. If it's false, then it does not. So the benefit to this is that it's more secure from message tampering. So let's take a look at HMAC in the Scrypt algorithm itself. So the first step it does is it creates an HMAC object without a key or data. So these values are now null. A key is hashed from the input password string, and the HMAC object is initialized with this key. So here we have that HMAC object, and now the key is a hash of that password. The data for this is still undefined. This will be added in the PBKDF2 step, which is the password-based key derivation function 2 step of the Scrypt algorithm that happens next. So now here's the overview of the algorithm. So now we can move on to PBKDF2. So just a quick review of the slide that we showed earlier for PBKDF. It takes in a salt, a number of iterations value, and a password, and it outputs a key password. In the Scrypt algorithm, it passes in the MAC object and the salt, and it returns a key, we're going to call it B, that is used in the memory hard function smix that follows. So let's consider this green square the outer loop, and the number of iterations is defined by certain variables, such as the MAC length. Inside of the loop is a pseudo-random function that produces a random message, and it feeds this message into the MAC, which every time the loop iterates, it also updates the return value B. So let's look at this part where it feeds the message into the MAC. So the MAC will now get this random message fed into it, and it'll perform this hashing function on the data. This continually starts to happen, updating the data with every single loop iteration. At the end, it just returns the value B after all of its hashing work has been done. So it applied a pseudo-random function that repeatedly applies the HMAC function with its key of the password to build the output key. And it returns a copy of the final key back to the main algorithm as B. So now that we're back at the Scrypt algorithm, we start a new loop. And this loop, the number of iterations of it, is defined by the parallelization parameter P that we defined earlier as one of the inputs into the Scrypt algorithm. And then the smix algorithm gets called. The smix algorithm goal is to be an algorithm which asymptotically uses almost as many memory locations as it uses operations, while making it impossible for a parallel algorithm to asymptotically achieve a significantly lower cost. So in other words, it requires a fair amount of memory to compute, and it requires an unreasonable amount of memory to crack. Custom-designed silicon chips, designed to run parallel processes, have no advantage to cracking this type of algorithm. So let's look at smix in more detail. Now I must warn you that this section of the presentation can get a little beefy. So what we're looking for here is just to see that it's hashing a value, and it does it in a very memory intensive way. So let's get started. So the smix algorithm takes in an input B, and it starts a loop. First it sets x equal to b, and it has two arrays y and z that it'll keep appending to as the loop goes through. So the first step of this top loop is the block salsa. So the developer of this algorithm needed a hashing process that is fast and does not possess excessive internal parallelism. So what that means is that the steps of the hash rely on each other in an iterative way, so that it cannot necessarily break off and branch into multiple processes to speed up the function. And it found this by using the widely studied salsa20 hashing function. After the block salsa block is complete, it'll set yi equal to x, which is the value in the array y that corresponds to the iteration of the loop, and it'll continue and loop until it reaches the end of that loop. Now it'll start a new loop, and it'll pass in the value x. The first step of this loop is to do an integerify, which converts x into an integer value. Then it'll run a Boolean algebra algorithm called block XOR. So what this does is it performs an XOR operation between values in x and b. The next step is to run block salsa again. And lastly, it sets the value z at I, which is the position in the array corresponding to the iteration of the loop, equal to the current x. And then when all of the loops are done, the loop ends, and then it sets b prime, which is equal to y appended to z. So that was just a general overview of the steps in this algorithm. Let's go into it in a little more detail. So the first step is it sets x equal to b, and then it starts the loop. And then it calls block salsa. So block salsa itself starts its own loop, taking in the value x. And then it performs block XOR, which takes the current value of x and it XORs it with values at b. And the I stands for the current iteration in the loop that it's in. Then it performs a salsa20 algorithm, which is a computationally fast hash, and it hashes the value x. And then the loop ends. So this will continue to repeat until it reaches the iteration limit of the loop. And then it goes back to the Scrypt smix algorithm. So then it sets the value for yi in the array y is equal to the currently hashed and XORed x, and then it does the loop again until it reaches the loop end. Now it starts a new loop, this time passing in x, and it'll do integerify, which simply takes the current value of x and converts it to an integer value. This integer value is used in the next block XOR algorithm as a position to indicate where it wants to XOR values between x and b. So it takes the current value of x and does an XOR on bi, I being the iteration value of the current loop. Next, it performs the block salsa again, which repeats the steps that we have up here. When that's done, it'll set a value for z equal to the current x, and it'll continue the loop until it reaches the end of that iteration set. When all the loops are done, it'll create a variable called b prime, and it's equal to the array y appended to the array z. However, b prime is set up so that the evens are first and the odds are after. So what this means is b prime is equal to b prime 0, b prime 2, b prime 4, b prime 6, etc. And when all those evens are done, it'll start on the odds, which is b prime 1, b prime 3, b prime 5, etc. So there you have it. smix is complete and b prime is the output. Now that is a pretty intense memory hard function, and there's a lot of steps that it goes through. And not only that, there's a lot of loops as well. So now we can go back to complete the remaining steps in the Scrypt algorithm. So before we do, what's our takeaway from smix? So that process might have been a little hard to follow and a little meaty, but what we want to say is that the process requires a relatively large amount of memory. This makes it memory hard, and this is one of the Scrypt's key properties. It also does a pretty good job at hashing the input b by using a widely studied and established hash function called salsa20. So we've just completed the smix, and that repeats itself in a loop many, many times, adding to the intensity of the memory hard function. Lastly, it performs another PBKDF2 algorithm. This time, it uses b prime from the smix as the salt, which outputs our final password key. So if we were to feed the word CS breakdown into the Scrypt algorithm, this is what the output would look like in its corresponding hexadecimal value. So there you have it. That's all for the PBKDF Scrypt algorithm. If you want to learn more, I strongly encourage you to download Colin Percival's paper titled Stronger Key Derivation via sequential memory hard functions. It's available online if you Google it, as well as on his website for his company, tarsnap.com. So there you have it. If you have any more questions, feel free to contact us at CS Breakdown, and have yourself a great day. Thank you for watching. Go to csbreakdown.com for more, subscribe to our videos, and like this. Bye.